everyone, this is Kang from Baidu Research. And today I and my colleague Xin Zhou are going to present this SoccerNet tracking tutorial. And I'll present about first half of this tutorial, talking about the data set and the challenge and the evaluation metric and the baseline methods. And my colleague Xin Zhou is going to talk about the some evaluation details and data analysis. All right, then first, apparently have a SoccerNet tracking data set and a challenge here. And this is sponsored by Baidu, especially Baidu Research. The entire project first initiated as a very good data set, and we turn it into a challenge this year. This SoccerNet tracking challenge is, as far as I know, is associated with the CVPR 2022 Activity Net Workshop as a guest task. And this tracking task, we designed it to be focusing on association instead of, similar to other multi-object tracking tasks that focus both on detection and association. Focus on association means that we gave the ground truth detections as a data input, so everyone can get the detection result. Actually, it's actually the ground truth annotations for detections, and you just focus on designing the algorithm to really track those moving objects, to really associate those bounding boxes. So that's one significant feature of this challenge. For evaluation, we mainly focus on the association performance as well, and we'll talk about the evaluation metric later. And in the future, actually, we're gonna evaluate on both detection performance and association performance as well. But for now, this is a relatively easier task, just focus on association. Okay, maybe we should talk about some application of the multiplayer tracking. Why we want to do this tracking challenge, because it has some really good application. First, if you can accurately track all the players on the field, you would be able to immediately visualize the team formation, the real-time team formation on the field. And sometimes that's a very good information for the audience, or sometimes the people who analyze the soccer data, they really need this information. And when you can really detect and track the players, and can even do 3D tracking, combined with some results from the camera calibration, right? You can do 3D tracking, and then on top of that, you can do some fancy special effect, like the one I show here on the right, some commercial software can highlight and track a certain player and visualize its the player's performance. Maybe it's good for training. And beyond that, multiplayer tracking can be some useful information for action spotting. In one of Silvio and Anson's previous papers, I think they mentioned about using the player tracking, player location information as the input. And this may help detect or recognize the actions happening on the field. Okay, apparently we have already some popular benchmarks on multi-object tracking. We have MOT 15 to MOT 17, and recently MOT 20 is also very popular, and a lot of participants. It's a very intense competition. And the figure here shows a curve on MOT 17, the performance on MOT 17 over the years. You can see that the performance steadily increases, and recently the #1 ranking method ByteTrack has been attracting a lot of attention. It's simple and efficient and gives very good performance. And apparently they can also be used in our challenge as well. As I said, a MOT benchmarks actually focus both on detection and association. I think, that said, one of the track of the MOT challenge actually allows the participants to use existing detection or given detections. But I think maybe more participants focus on using their own detectors, private detectors, to achieve a better performance overall. So what is the evaluation metric here? I mentioned that we're going to be focused more on the association part, right? So the reason there is a new evaluation metric that is being advertised and being recognized in the community. It's called HOTA. The paper's reference is listed here. And HOTA essentially is a metric that has a perfect balance between detection performance and association performance. The metric here, the metric itself can be decomposed into something called data and ESA. Data focuses on detection performance, while ESA apparently focuses on association performance. This figure is from the HOTA paper. Here's a simple example. Say we have a tracklet, ground truth, and A, B, C are three different tracking results. A is like the tracklet has 50% overlap with the ground truth. B actually has a switch, ID switch in the middle, and the two sub tracklets each has 35% overlap. Well, C has too many switches, but since the entire the detections together overlap with the ground truth, just the ID switches too many times. So if we apply the data evaluation metric, which only focuses on the detection, the method C actually gets 100% detection accuracy, intuitively, right? And because only has ID switches. Well, method A gets 50% accuracy on the data metric, because the other half is lost completely. On the other extreme of this metric, ESA, we can see that it focuses mainly on the association part. Method C gets too many ID switches and it gets very low ESA scores, even though it has very good detection performance. And method A is 50% overlap. Tracklet with the ground truth gets 50% association score, and it's reasonable. And the HOTA actually is in the middle of the spectrum, right? It's a perfect or a even balance between a data and ESA score. So if you have a detection error or tracking or association error, they will be reflected in the HOTA metric compared to our previous popular metric, MOTA, which is more focused on the detection and sometimes are not ideal in terms of not correlated with our human feeling or subjective performance evaluation. All right, we use HOTA for our challenge, and now we can have a deeper look on the statistics of our data set here. Apparently, we have a data set composed of many short clips of soccer game videos. And in those soccer game videos, we have tracklets of both players and referees, and also the ball, the soccer ball. In total, we have those clips from 11 games. From these 11 games, we select 200 clips, each of 30 seconds long. Each clip is centered around, maybe not centered, but it's around key action spots. Actions like goal, substitution, and clearance, red card, things like that. These are called key actions. And we selected those short clips around those key actions so that this tracking clips can reflect a good distribution of this soccer game dataset. Beyond those short clips, we also have 12 complete soccer games recorded during this 2019 Swiss Super League. Complete soccer games, we mean the camera is the same, and from the beginning to the end, same camera. And it's a very long game, and we actually don't use this long, complete game videos here. And in the future, maybe next time, we can provide a really long, like maybe even something that can reach up to 45 minutes long game recording for really long time tracking evaluation. Yeah, but for now, we just have 30-second long clips for evaluation. And these 200 clips are evenly divided into, almost evenly divided into 4 quarters. I think for this challenge, we use 1 quarter for training, 1 quarter for validation or tests actually, and another quarter for challenge. And then the 4th quarter is remained for the future challenge. Okay. Here is some comparison to other data sets. Here we listed the MOT data set and some other maybe single object or multi-object data sets. Sequence-wise, apparently we have more than any other. We have more than 200 sequences, and that's most. And frame-wise, we have a lot, but not the most, right? Apparently, the Tau dataset has over 4 million, which is most, and the second is ours, has about 200K. And track data-wise, we're also not bad. The first has 16K, and ours is 5K track rates, and we're just second best. And the bounding boxes will really devote a lot of resources, so we get the most bounding boxes here, over 3 million. And the domain, apparently we are in the soccer domain, and others are maybe some detecting pedestrians on the streets, some are for autonomous driving. And the only other soccer domain data set is SSET. Okay, that's the statistics. What about some properties, some subjective impression on this data set? Here's a list. First, compared to other multi-object tracking data set, an immediate difficulty would be players on a soccer field, they wear similar uniforms, right? So player appearance would be very confusing. So there's going to be a very little difference between players, especially in the same team, right? And the second, on this data set or on this challenge, we require participants to be able to re-ID the players in terms of this case that when a player leaves the image or the camera, and return later, the ID should not change. You should be able to re-identify the player when it leaves temporarily. And the third difficulty could be other participants. Here it means not just a player, not just the referee, some other people like the coach or other personnel around the soccer field, or sometimes there is audience in the background. But for the convenience of this challenge, we provide ground truth detections already. Those detections are already ruling out some other distractors. So you can just only use detections, and it will automatically filtering out a lot of the distracting noises. And next, the a very common problem is the fast motion. It is also presenting other types of data set. But here in soccer, when players start running on the field, it's going to be a headache, and fast motion causes a motion blur, right? And it is a trouble for both tracking and also the annotation as well. Yeah, later I'll talk about some annotation errors, actually. Last but not least, the collusion scenarios. When players gather together, they have intense competition or even fight for the ball. We have very severe collusion scenarios, and it's going to be a very challenging task for the multi-object tracking, and it's worth studying as well. Okay, here's some visualization. The annotation, actually, we can guarantee that the annotation accuracy is about 95%, but due to the amount of data, large quantity of the data, the frames and the objects in the data set, apparently there is some noises, errors. Right here, we show some annotation errors when there is fast motion in the field. Actually, when we annotated this data set, we annotated those keyframes by hand, and some of the frames are interpolated. So when there's fast motion, interpolation is not accurate, so the bounding box is a bit off. So here on the third row, we can see that on the right bottom, apparently some bounding boxes are deviating from the players. But these cases are only a small portion of this data. So just keep in mind that there's some errors. Okay, let's talk about baseline methods. The baseline method actually are already provided through our SoccerNet tracking dev kit on GitHub. And here, let's talk about the Deepsort and FairMOT. And FairMOT is actually not provided really. And we provide Deepsort and the ByteTrack. First, the Deepsort method is a very popular and effective method. I provided the references here below. And Deepsort is built on top of a sort. Sort is just a simple online and real-time tracking the user comment filter to predict the states of those track bounding boxes, and the user's Hungarian method to match correctly and then the detection. While Deepsort actually is the first to use the convolutional network to extract appearance information and to actually build a reality extractor. And this reality branch or reality model is actually pre-trained on a large-scale person reality data set, and it kind of provides a useful encoding on those tracked object. And apparently this part can be trained But as someone actually asked on the Discord channel, how to train those provided baseline. Unfortunately, here it's difficult to benefit from training because apparently Deepsort already trained its ReID model on a really large ReID data set. And if you really want to train or fine tune on the SoccerNet tracking data set, you have to manually create a ReID data set. You have to crop those players, right, and create your own ReID data set on our SoccerNet tracking. So it's quite some work. All right, second baseline, FairMOT. FairMOT actually is a very popular method in the multi-object tracking field before ByteTrack. And it is based on the joint detection and embedding idea. And it actually uses a encoder and a decoder backbone, I would say, to extract a feature map. And then this feature map can supply the features for both the detection and the ReID heads. So it's just a one-time pass and you get both the detection and the ReID features. And it's so it's fast, it's neat, and it's effective, but it's not really friendly to our participants here for this challenge because it's hard to really train FairMOT on the data set using the given ground truth detections, right? Because here you can see FairMOT actually gets the detection and ReID features at the same time. It's not isolated like other methods. Some other methods, they have isolated stages for detection and ReID feature generation. Isolated, I mean, they first run some detector and then get bounding boxes. Then on those bounding boxes, they run some ReID extractor to get a feature. Two isolated stages, and each stage can be swapped to some other models. But here, FairMOT, it's a joint detection and embedding. So it's really hard if you use your ground truth detections. Really hard to find correct matching between the ground truth detections and the ReID features. Yeah, it's doable. I personally actually examining the code. It's doable, but it's a little bit tricky. So we don't provide a FairMOT in our official baseline. Yeah, but it's really good to know this method, especially in the future. You may want to train a FairMOT for both detection and association when the ground truth detection are not available. You can do that and may get very good performance. All right, the third baseline is ByteTrack. ByteTrack is essentially simple and effective. It's comprised of a strong object detector, YOLO-X. It's a really strong, really efficient. It achieves a very good balance between speed and accuracy. This YOLO-X detector is trained on multiple detection data set, I would say, Coco and some others. And it's really transferable, actually. It can be directly applied to the soccer scenario and it works very well. Not just on players and also on some other personnel like audiences. Besides the object detector, it also has a clever or insightful data association method. They call it Byte, but I have no idea why it's called Byte. It's not even a short name for some detailed algorithm. Just call it Byte. Now, what is Byte? So Byte is actually quite simple. It contains two steps. First, just associate your high score detection boxes to the tracklets using IOU distance. In this step, some tracklets are unmatched due to occlusion, motion blur, or size change. But on a second step, you associate low detection scores, low detection bounding boxes, low score detection bounding boxes with these unmatched tracklets to recover some of these detection bounding boxes that you may lose in other tracking methods. But in this method, those low score detection boxes are fully utilized and get matched with tracklets and can increase the performance a lot. Simple as that, just 2 steps. All right, then, so what about the performances of this baseline? Okay, I'll have my coworker Xin, okay?
Okay, so what we're looking at here on this table is our experiments for the baselines. So to summarize the table, we can see that without ground truth, Deepsort performs worse than FairMOT, and it's also FairMOT is worse than ByteTrack, which is a generalization of the results we see on the MOT challenges. And then for what is more relevant to us, so with the ground truth, so Deepsort performs slightly worse than ByteTrack in ESSA. So like association is what we're interested in. And then so another thing to observe is that even with ground truth, like detection is less than 100% because the algorithms filter out some of the detections in the association process. And then another thing that we can see is relevant is that when we fine-tune FairMOT from end to end, so first of all, both the detection and the association performances increase because the FairMOT wasn't trained on our data set, and then like in the fine-tuning, like we observed that like more audience get filtered out, and then also we can detect the ball, and then so it seemed to close half of the performance gap between with or without ground truth. And then we also observed that kind of association and detection are related because in the association process, we also kind of filter out or do things with detection. So it's like the association process is kind of tied to detection. Okay, next. Okay, so this slide, I basically summarized what I said before. And then the things to note is that with ground truth, ByteTrack seem to be slightly better than Deepsort. And then we will have less than 100% detection even with the ground truth. Okay, next one. Okay, so in the next slide, we have a performance by action category table. So so in this table, we break down the metrics for each action class. And then so again, so let's just focus on the with ground truth part, which is part of the challenge. And then you can see that with ground truth, so the best detection goes to substitution, and then the bad ones are the goals and the clearance, and then the good association also goes to substitution, and then the worst is the corner, is a corner action. And then so in this, again, I think so we mentioned previously in one of the previous slides, so the difficulties we think in these categories are 2 things. One is the fast motion, because like the further away your detection box is from your original one, then you're depending more on some sort of like re-ID capability instead of just like IOU. And then the second is occlusion, because so when you have a lot of occlusion, like which is what happens in the corner case, because everyone's basically in the in front of the goal, and then in that case it's very hard to determine like the tracked IDs for each tracklet, and then so the substitution action is the easiest, is because when there's substitution, then everybody's moving slow, so we don't have as much fast motion, and then also people are kind of like standing apart, so you're not running into the occlusion situation. Okay, so next slide. So again, this is a summary of the results we can see in the previous table. So with ground truth, so detection is negatively impacted by fast motion. So the good cases are in substitution, and then the bad cases are in goal and clearance because they're moving like very fast. And then also, so in association, the good case is again substitution, and then the bad case is corners because everybody's gathered together. Okay. And then I'll skip the without ground truth part. Okay, so this is just a diagram visualizing the results we see. So the blue dots are all without ground truth, and then the orange dots are the with ground truth. And you can see that, for instance, for detection with ground truth, they're kind of about the same filtered by the association process. So you lose the kind of around the same amount of like ground truth bounding boxes in the association process, but like the association itself, it varies by category from the easiest for substitution, and then yellow cards because it's again like people are more apart, and then down to like the hardest is a corner, and then like shots on targets and foul, and then in those cases people start kind of getting concentrated. Okay, and then here we also I think so this might be a pretty like specific and useful slide for further improvements. So so for the data and ASA metrics, there are further breakdowns, which is called like data recall, data precision, and then ASA recall and ASA precision. And then we can see that, so for instance, for substitution, both the recall and precision are the best. So again, let's look at the with ground truth cases. And then, so for ASA, both recall and precision are very good for substitution. And then, so remember our bad case of corner, and and then we can see that again, kind of both recall and precision are bad. But I think recall is like slightly worse in comparison to, because for instance, like precision, they're all like around 88 or 85, like from like 85 to 90% kind of range. But like, I think the range for recall, there's more room for improvement. For instance, some of them are in the like low 50s, and then some are in 60s, and then up until substitution, like it's in the 80s. So like my interpretation of this result is that so there's more kind of improvement potential for like as a recall. And then also I think there was some discussion of, so what are some simple strategies to kind of to help get people started improving upon the baseline. And then from what I, again, like from what I said, there are two difficulties, right? One is kind of occlusion, and then the other is fast motion. So for occlusion, I'll just mention one of the simple things I observed with the ByteTrack baseline is that, so there was a parameter for match thresh. Basically, it's a threshold for okay, when do you start making like 2 bounding boxes to like assign them to the same tracklet? And then in my experiment, so like the official baseline had like two choices. One is to have 0.7, and then the other is to have 0.8. And then in my experience, the higher one helped improve the statistics, which means my interpretation of that is, so for a very simple thing, like if you have like a more strict like match thresh, then it helps you in the occlusion cases, because now you're requiring more overlap for the bounding boxes. And then another way to improve maybe, okay, so now when you do the assignments, if you can somehow involve the features, then like between the bounding boxes, then it's better for occlusion cases. And then for the strategy for like increasing your performance in the fast moving cases, now like it's my pure speculation, but I think so there are hyperparameters, like mentioned in the previous slides for the algorithms, like there are hyperparameters controlling like the search radius for your next bounding box to match, right? So in order to deal with the fast moving cases, that's something you can look at to tune to increase your range. And then also, so again, like with increased range, maybe there's things to do to kind of improve the re-ID or like the assignment process. For instance, like in Deepsort, the Hungarian method is used, to provide better matches. So maybe you can try to like use that for more boxes, and then try to use that to increase your recall ability. So both increase radius and then trying to match more boxes so that your tracklets are more consistent. Okay, so I think that's all I'm gonna say. Yeah.
So let's thanks again the speaker, Li and Xin. Thanks a lot for your presentation on player tracking. I hope many of you will participate in that challenge as well. This is our latest task that has been released only 2 weeks ago or 3 weeks ago. So please feel free to participate. Thank you.